Hello everybody, I'm here on the CFD Direct page on the User Guide 2.1 Lid-Driven Cavity Flow tutorial. This is just a simple simulation, and it's a good starter tutorial for anyone trying to understand OpenFOAM. I just saw that this was on the OpenFOAM Wiki's tutorials page in the first Glimpse series as their second entry, Lid-Driven Cavity. So I saw that there was a video up for this one, so I wanted to put up my own video for this. Moving on, this tutorial will describe how to pre-process, run, and post-process a case involving isothermal incompressible flow in a two-dimensional square domain. It is shown in figure 2.1. It's got these three stationary walls and a top wall moving at 1 meter per second in the x direction. Initially, the flow will be assumed laminar and solved on a uniform mesh using OpenFOAM, which is for laminar isothermal incompressible flow. During the course of the tutorial, the effect of increased mesh resolution and mesh grading towards the walls will be investigated. And we're going to increase the Reynolds number, and we're going to use piezo foam instead because that's turbulent isothermal incompressible flow. So as we can see, there are multiple solvers for OpenFOAM depending on the type of flow you have. So make sure you choose the right one when setting up your own simulations. Pre-processing. So cases are set up by editing case files. So what you're going to want to do is take the folders that we're going to want from the installation directory of your Blue CFD, if you're on Windows, that is. So I have mine in program files. You're going to go to Blue CFD, OpenFOAM 5.x, and then tutorials, incompressible, OpenFOAM, and then cavity. This is where they all are at. So I copied all three of these because we're going to need all three of them, and I've just put that on my desktop just because it's nice to have it isolated from everything else. We're going to be making copies of these, and we're going to want them to be isolated. If you're on Linux, actually, make sure you just follow all these as said, because these are all Linux directory in Linux terminal commands, so I wouldn't know. We got mesh generation. OpenFOAM always operates in a three-dimensional Cartesian coordinate system. You can instruct it to solve in 2 by specifying the empty condition on the boundaries normal to the third dimension. So this cavity is going to be a uniform mesh of 20 by 20. That's what we're going to do, and that's shown by figure 2.2. This is the block mesh dict, which defines the block mesh, which is your domain of solution of your flow. So anything inside this domain, we're going to be solving flow for. This convert to meters entry. The base unit you can say is the meter, so 0.1 would indicate 1 times 0.1 meters, which is a decimeter. If we wanted this to be in the centimeters, we'd put in 0.01, millimeters 0.001. If we wanted inches, we put in 0.0254. Vertices, this indicates the position of each of the vertices. So the first entry right here would be 0.0, and that is at the origin. 0.1 is located at x equals 1, y equals 0, z equals 0, and that's shown as here. It corresponds to this diagram rather well. We can see that these are, it's a box because the x, the first 4 entries, their x and y entries, are identical to the second 4, except their z values are increased a little bit. Blocks indicates how many separate blocks within our mesh we want to have. So in this case, we only have 1 block, and it's going to be 20 by 20 because that's what we want. And we'll visit grading in a little bit. But edges, this indicates where you want to put in splines if you want to have splines in your geometry and you're making your own in OpenFOAM. So this is where they would belong if you were generating them from a MATLAB script, perhaps. But we're not messing with that right now. Boundary, it sets the type of boundary each of your block mesh boundaries are. Like what kind of properties do you want your boundary of your block mesh to have? So the moving wall is going to be a wall, and we're separating them into categories as well. We're separating them into which walls are different from each other. Fixed walls, these are all the fixed walls, and those are indicated by these faces right here. Moving wall, there's only one of those. So only one of the faces is going to be the moving wall. The order of these numbers matters. 3762. That is in a counterclockwise direction. If you're viewing from the outside, 3762 defines the top face. You can also say that it's clockwise from inside if you're viewing from inside the cube, but I think it's a bit more intuitive to think of it as viewing from the outside, because that's how we normally view things. You can see that this applies for the fixed walls, say like 0473, 0473 for that face, and so on and so forth. We can see that the front and back is the empty condition. This is what makes it a 2D simulation, and we'll see that employed multiple times throughout this code. So we can run this block mesh. We're gonna actually copy this and rename it to cavity post geo. Cavity post geo, because I want to keep the original cavity. So we're going to type in block mesh and create our block mesh. We can view this a bit early. Parafoam. Hit apply right here to view the geometry. And if we want to see our block mesh, we can go to wireframe. So as we can see, there's one cell in the Z direction, and we got a square 20 by 20 geometry right here. You can change the representation up here. You'll get more accustomed to ParaView's interface as we use it, but take a look at it now while you can. Avoid scrolling. As you saw there, I changed the representation here by scrolling. I use this to move up and down. If we scroll, we can end up changing values, as you see here. If you scroll over this, see, it's messing it all up. So we're just gonna exit out of this before I keep messing things up. Boundary and initial conditions. So we want to look at the 0 folder. And we got P and U. So P is right here. Its dimensions. These entries go by kilograms, meters, seconds, Kelvin, moles, amps, and candelas. Just the standard SI units. So that indicates this is meters squared per second squared, which is not what pressure is. This is kinematic pressure, which is pressure divided by density. So just keep that in mind. Internal field, this has a uniform 0 value as an initial guess, because we need an initial guess just to initialize the value. Boundary field, these are the boundary conditions. So moving wall, that's our top wall. Its boundary condition is going to be a 0 gradient. So the rate of change of pressure along the wall is going to be 0. And that is the same case for the fixed walls. So it's a good boundary condition to have for a wall. And front and back, it is empty, as we saw earlier. If we check out U, we can see that it is meters per second. We have an initial guess of 0. And our boundary conditions here, the moving wall, it is moving at a value of 1 meter per second in the X direction. It's a fixed value. Fixed walls, they have a no slip condition, so I assume that they're staying still. No slip boundary condition, and front and back are empty. Physical properties. So for the OpenFOAM solver, we only need transport properties to define kinematic viscosity, which is new, which is that in the Reynolds number equation. So if we go to constant transport properties, this is where it is. We can see that new is here, meters squared per second. It is at a value of 0.01, and we are getting a Reynolds number value of 10 because of that. We have a D equals 0.1 meters, U equals 1, and if we want a Reynolds number of 10, we will use a viscosity of 0.01. That's a rather low Reynolds number, but we'll see more about that in a bit. Control. So this is going to be dealing with the control dict. if we go into System, Control Dict, this is basically how the simulation is run. It's the control. It's the control dict. You can see which application we're using, OpenFOAM, when are we starting from, when are we stopping, what's our delta T. We're going to have to keep these values in mind when we're considering things like the Courant number. It has to be less than 1. So we calculate our delta X, we calculate our delta T to make sure that our simulation is valid. To achieve temporal accuracy and numerical stability when running OpenFOAM, a Courant number of less than 1 is required. So make sure that you follow that. Discretization and linear solver settings, those are found in the FV schemes and the FV solution files right here. So we can see we have like the Euler method, Gauss linear method, and in here we've got tolerances. We got the Gauss-Seidel solver, we got other tolerances. So if you want to mess around with your tolerances, this is where you would go, or if you want to change your solvers. So we want to view the mesh again, I believe. Actually, we're going to run OpenFOAM real quick because that's what it wants to do next. So OpenFOAM, there we go. It doesn't take too long. And we're going to view these results. And if we hit apply, there we are. We have some colors. We can change which parameter we want to view using this drop-down menu. So right now we're in that kinematic pressure, but if we change to U, this is going to be our velocity. Very cool, very cool. Right here we can change the preset. Yours probably is not the blue to red rainbow like mine right now. I changed my preset, so if you want to change your preset to that, I think it's the easiest one to interpret, so you'd hit that and apply. These buttons rescale the data range and rescale the custom range. Those are important. If you know what sort of bounds you want your U velocity to be within, you'd hit these. And you can also change the view from here as well. What else do we got? So we want to bring it to t equals 0.5 seconds. This is where we change the time. And we want to cut a slice out of this. Wait. So if we're going to cut a slice out of this, we're going to go to Filters and Common and Slice. And we're going to change this to the values that were on there, which were 0.05, 0.05, and 0.005. Get rid of that. And we're going to make this Z normal, which is the equivalent of that, 001. We're going to hit apply. What's happening here? Alright, the wireframe is what's getting in the way. That's what's happening. We change this to surface and just go to slice. Oh boy. Okay. We're going to delete this real quick. We're going to leave that there. Then we're going to reapply our slice. This is just one of the annoying things that you have to deal with. So we're going to change this to a Z normal, and we're going to change these values once again. 0.005. Apply. And we're going to apply. There we go. Now we have a two-dimensional slice. We can change this to U. And we can create contours as well. We can apply the contour filter. Going into filters. And we will go into common contours. And it wants us to put 10 points down. So let's go 0.1. I'll go 0.2, 0.3, 0.4. Bear with me. All right, and hit apply. And we can see that we have a contour of different values here. And these are in P, and that's the only thing we can contour by at the moment. Unless we change it to U. All right, yeah, that changes it as well. So now it's contouring by, still contouring by P, but now we have the U values here. We're going to delete these now and move on to a different filter. We're going to be doing vector plots now. This was really confusing when I was going through the tutorial. I was like thinking that these figures would be for contours, and I don't read, so I didn't see that this was for the glyph filter. I'm like, these aren't contour plots, these are vector plots. So these are not the vectors for contours. These are the vectors for vector plots, or the figures, excuse me, for vector plots. So it wants us to remove the other modules, as we have done. And we want to select the cell centers from alphabetical. Alphabetical, cell centers. We want to apply. Do not fear. Just go to common and then glyph. And now if you hit apply, we now have these vector plots, or vector plot. We want to change this to 0.005. And we can change this to velocity by changing, we are going to coloring, glyph scale, that's for the scalars, glyph vector, that's for the vectors. So we can see that its speed is fastest at the top next to the moving wall, and it also moves in this swirling motion, which would make a lot of sense. As the moving lid, it causes the flow to circulate. A lot of this is telling you about the different features of pair view. So if you want to learn more about it, I believe this is also for the stream tracer filter as well. So that's streamline plots. Does it want us to do more for the vector plot? No, I don't think so. Streamline plots. So we're gonna delete our two filters right here, and we're going to be applying the stream tracer filter. We apply. We want to change this line right here, the high resolution line source. It's going to run from 0.50, 0.005 to 0.05, 0.1, 0.0005, or 0.005. Yeah, that's what I said. So 0.05, 0.005 to 0.05. 0.1, we can delete all of these, and 0.005. And we're gonna hit apply. Okay, what's wrong here? This is wrong. Right there, and we're going to change resolution to 21 as it said. We're going to change this to velocity as well, change the coloring from P to U, the point U, and looks about right. Perhaps a bit different, but they have some different parameters here. Clicking apply, the tracer is generated. We should then select tube from the filter menu. So let's select tube, see what it does. If we apply, oh my goodness. Looks like it just makes tubes out of it. I don't know if I like that. Maybe if we reduce the radius of these tubes. Okay. Okay, I get it. It's not too bad if we lower the radii of the pipes, but... So that's the streamline plot. So increasing the mesh resolution. So we're going to be increasing it by a factor of 2 in each direction. And we're going to be mapping the results of the coarser mesh onto the finer mesh. So we're going to take our old case cavity and turn it into cavity fine. So we're gonna just create a new folder. That's not what it does. This is what a new folder is, cavity fine. And we're gonna copy system and constant from postgeo into here. Are we gonna need a 0 folder? No. We're gonna take the 0.5 folder. That's what we're gonna be doing. All right. So we're gonna be going into system, block mesh dict, and changing this to 40 by 40 by 1. Save that. And then we're going to run block mesh. Are we already in cavity fine? I don't know. Cavity fine. Block mesh. And we'll hit parafoam. See how this turns out. A wireframe. This looks like a 40 by 40 grid to me. So we're just gonna move on. We're gonna map the coarse mesh results onto the fine mesh. We're gonna be using map fields. This is kind of a pain if you don't follow your instructions perfectly. So be careful with this. So we need to go into our control dict in cavity fine. And we need to change our start time to 0.5. And save. We're ready to run map fields. So we're gonna go back to our terminal. And we're gonna run map fields .. and we're gonna do cavity postgeo. That's what we're gonna change from theirs. Okay, I don't have a map fields dict. So while I was trying to figure that out, it just decided to work for me. It came out correctly with the interpolating P and U. So we're just going to view this in parafoam real quick. So we're going to hit apply. And there we are. If we go into wireframe, we'll see that we have that same 40 by 40 grid. Can change this to U. Same deal. We're going to exit that for now. We need to be making some control adjustments. So we need to maintain a core number less than 1. And we just reduce the size of all the cells. So we must reduce the time step by half the size. So we will be going into this control dict in system and changing our start time. First of all, this needs to be, oh goodness. We are a bit behind. Oh no, we're in cavity postgeo. Apologize. We're going to be going into cavity fine, system, control dict. We start at 0.5. We need to be changing our delta t to 0.0025. We need to be changing right interval to 0.1, 0.1, and right control to runtime. We're also going to change the end time to 0.7 seconds. Now, hopefully I got all these mapped correctly. Now it wants us to run OpenFOAM as a background process and to output a log file. So we're going to input these commands and cat log. And if we go to our folder right here, we'll notice that we have a log file. If we want to open this case up in parafoam, we can do that. Hit apply, you can hit wire mesh, and there we go. So now we're going to be doing vector plot with refined mesh. We're going to open multiple cases simultaneously, so we're going to show both the refined and the original mesh at the same time. So what we're going to do is we're going to go into PostGeo and type parafoam-touch like we see over there to create a OpenFOAM case of it. Then we're going to be continuing with making the vector plot of the one that we just did, the fine case, the fine mesh. I'm just fat fingering everything right now. If we go into cavity fine, we can hit parafoam. We can show this first mesh. We can make a glyph, a vector plot out of it. Vector plot here. And if we hide that real quick, we can open the other one that we have in cavity PostGeo. We can apply that as well, and we can apply the same sort of magic that we applied on the other one. Recent glyph. There we go. So we have glyph there, and we have glyphs there. We can, if we want to get another layout, we can try this. Glyph 1 right here, and then glyph 2 there. Moving along, we're going to be going into plotting graphs. So we can see what sort of functions that OpenFOAM offers to us by typing in post-process list. And this is all the different functions that it has to offer for us, but right now we're just going to be using the components function on the cavity and cavity fine cases. So we need to be going into the cavity, or we're going to be going in the PostGeo cavity folder. And then we're going to be hitting post-process components U. Oh, that's not what I wanted. We're going to be going into desktop, PostGeo, and we're going to be opening this post-process func components U. And that maps the X, Y, and Z components of velocity to the time directory. So we can view this in paraview, parafoam, and we can see that our cell arrays, they include U, UX, UI, and UZ. So if we change this to U, or what is it? We go into filters, data analysis. Is that what we're doing? Plotting graphs. Yes, we're going to go to plot over line, filters, data analysis, plot over line. We're going to go from, where are we going from? 0.05, 0.005 to 0.05, 0.01, or 0.1 to 0.005. 0.05, 0, 0.005, 0.05, 0.1. Why am I hitting commas? My goodness. 0.1 and 0.005. We're going to apply, and we get these graphs right here. Resolution can be set to 100. So let's set this to 100 real quick. Apply. So arc length, that's going to be our x-axis. That's the arc length of our line right here. So that corresponds to the y direction. Everything in the y direction, 0.1 meters. That's where the top is. And if we're going to copy this graph right here, we're going to want to scroll down to the series parameters and unclick everything but UX. And then we're going to want to highlight UX and then go down here, get rid of the line style and change the marker style to square. Now, it's not exactly the same as that because the scale is a bit different. It's a bit scrunched, it's a bit narrow. It needs to be a bit wider if we want to get that same sort of scale. But we can also add these axis titles, velocity in the x direction, and that's meters per second. And we can also change our bottom axis. We can change this to distance from cavity base, as it says down there. Cavity base, and that's in meters. And we have a nice little plot. Moving along. Introducing mesh grading. The error in any solution will be more pronounced in regions where the form of the true solution differ widely from the form assumed in the chosen numerical schemes. So, error is where the true solution is different from the calculated solution. And this error decreases with cell size, so we're going to introduce mesh grading to get a finer mesh and reduce the error in our solution. So we can see here that the variations in velocity can be expected near a wall, and we can retain the same number of cells while also making the cells smaller in that region. So that's how cell grading works. We can keep the computational cost relatively low and still get greater accuracy. So we're going to be going into the cavity grade case, which we have right here. It requires a lot of block mesh sticked editing, so they've done it for us. And it's representing this geometry right here. It's the same one shown from above, except it's broken up into 4 different blocks. As we can see, these we've got 18 different vertices right now. We added all of these different 0 to 17 vertices, and we created different blocks out of them, each of them with different grading. We're going to see it's difficult to show or explain the effect of the grading through the numbers, but it's the ratio between the largest and smallest cells. However, if we go into block mesh, we run block mesh on this and see what the geometry is like, we'll get a better idea. So we're going to go into cavity grade. I'm going to copy it and make post geo. Cavity grade, post geo. And we're going to open this and hit block mesh. Parafoam. Hit apply. And as we can see, the corners, the cells are smaller in the corners. Starting at the origin, your cells are going to be the smallest size, and by the end of your by the boundary of that block that we have, so say we have block 0 right here, from 0 to 1, the cells are going to be smallest next to 0, and they're going to be largest next to 1, and the ratio between the largest and smallest cell at 0 and 1 is going to be 2. The block at 1 is going to be twice the size of the block at 0. And that's best shown here. Because of this, we're going to have to change our control dict, because the Courant number is going to be, it's changed now because of our delta x has changed. So we're going to have to change our delta t to 2.5 milliseconds and change our right interval to 40. So we can do that real quick. Post geo, system, control dict. We can change our. Is this supposed to be at 0.5? I guess so. Oh no, I'm in cavity grade post geo. Where am I in here? This is. Let me make sure I'm in the correct one. Cavity grade post geo, correct. So we're going to have to change our delta t to 2.5 milliseconds, which is correct, it seems. Right interval has to be at 40. That's correct. So yeah, we're all set. We're going to map fields now. We're going to map fields the final results on cavity fine to cavity grade. So we're going to open this in terminal. And we're going to do map fields / cavity fine consistent. We got the correct output right there, and we can view the results for this case with parafoam. Can apply. And we can view U. And we can see how the different mesh affects it, I suppose. It doesn't seem to be too different because it's not that drastic. I'd assume it's not the craziest simulation. We don't really have too much variance in time, so it's not, I don't think that this mesh grading is going to be insane. So, and we can still, this is not a crazy mesh. This is not a very fine mesh, so, and it's not a crazy simulation. Increasing the Reynolds number. So we've only had a Reynolds number of 10, which is really low and leads to a stable solution quickly. So we're going to change our kinematic viscosity in the transport dictionary in this new cavity high Reynolds number case. So we're going to copy this post geo, rename it to cavity high RE, and go into its control dict. We're also going to delete those files. Control dict. Oh, sorry, transport properties, not control dict. I apologize. We're going into control dict in a little bit, but transport properties is where we want to change our kinematic viscosity. We're going to save that. Now we're going to go into control dict, and we see that we want to change start from to latest time. Latest time. And we want to stop at end time of 2. And I believe that's it. And we run OpenFOAM for this case. Have I run block mesh on this actually? Yes, I have run block mesh on that. So we're solving OpenFOAM and it's all set. And we should view these in parafoam. We'll exit out of this and hit apply. And we will view the glyph vectors if we apply the same sort of filters. Once again, glyph, apply. And this is different. So earlier we saw that the vectors, the glyph vectors down there, they were not behaving like that before. So I guess we can see some effect of the higher Reynolds number right there. That was not there. Anyways, let's see what it wants us to do. It's telling us that we're going to be using piezo foam now, I believe. So we're going to copy the cavity case in the piezo foam directory. So let's go into C, program files, blue CFD, OpenFOAM, tutorials. If we go into compressible, incompressible, I apologize, piezo foam, laminar, RAS, excuse me, cavity, Control C. We're going to make a copy of it right here and then rename it cavity RAS, which stands for Reynolds Average Simulation. We're going to copy this and put it into desktop. We can generate the mesh, the block mesh, if we exit out of this terminal right here. We'll hit block mesh. Mesh grading towards the wall is not necessary when using the K epsilon model. This goes into the derivations of K, which is your kinetic energy, and epsilon, which is your turbulence dissipation. So this goes into a lot of the theory behind it. Make sure you know this, but it goes beyond the scope of my knowledge. So we're going to move on. We're going to want to change the transport properties. So we're going to go to constant turbulence properties, and we're going to, transport properties. And we're going to change it to 10 to -5. It's already there. So we're going to go to system control dict, and we're going to change delta t to 0.005, as well as, that's it. We're making the current number, satisfy the current number restriction, and end time to 10 seconds. That's what we need. So end time 10 seconds, everything's already set up for me. Wonderful. We're going to execute piezo foam. Taking longer this time, not too long. Parafoam. And this is much different. As we can see, the different solvers can cause wildly different results, as well as the different flow that we have as well. So these cubes, they show these dots, actually, they interpolate in between the cell walls, while these blocks, these are just the cell at the cell walls, or what the value of the cell is, excuse me. So we can change this back to U, and we can increase, we can see how the flow develops like that. We can see there's a sort of vortex forming. So if we go back to the beginning, you can see it spirals into that. So we're going to be changing the case geometry. Oh, actually it wants us to change to 20 seconds, it seems. So we can do that. I'm interested to see what happens when we go to 20 seconds. So we'll change this to 20. We'll save. And we will rerun piezo foam. And we will run parafoam once again. We're going to give it some more time to play out. So that's the pressure. If we go to U, let's go to the beginning. More or less the same thing. So we want to deal with cavity clipped. If we deal with cavity clipped here, if we look at its block mesh dict, we'll notice that a square of length 0.04 meters has been removed from the bottom right. So these vertices indicate that geometry, and we can see that it has been created into 3 blocks, indicated by those vertices. Boundary conditions indicated by those faces, and we can generate the mesh with block mesh. So let's make a copy of this. Cavity clipped. Post geo. Open that in blue CFD, and we can do block mesh. Now we can enter parafoam to take a look at this geometry. Hit apply, and there we go. We see that it's the same sort of geometry we had before, just with a little square cut out of it. Moving along. We want to copy the 0.5 seconds folder from our cavity post geo, I believe. So we're going to go to cavity post geo and copy, incorrect. We're going to copy that into cavity clipped post geo. We wish to map the velocity and pressure fields from cavity into the new fields of cavity clipped. So we have our map fields dictionary. I hope. Map fields dict. And we have patch map lid moving wall. So I've been having a lot of trouble with this. We're going to see if this works to be able to map these results on top. So I'm getting a lot of errors where this map fields dict doesn't seem to be read by OpenFOAM. But we can try and get this solution here where it's the actual solution, not the mapped solution from Cavity. So our parameters are all set. So we just have to run the map fields utility, Cavity, postgeo. So size 400 is not equal to the given value of 336. Is 18 times 12 336? I'm going to do a quick calculation real quick. 18 times 12 is 216. No. So we're good. We're going to skip this right now and just go for IcoFoam. Okay, it doesn't want to do that either. So we have something going on. Give me a second. We'll get this figured out real quick. Alright, apply. And of course, I hate how this happens, but alright, we're gonna see the glyphs to make sure that this is right. Okay, of course. I really hate that this happened, but I just changed things up and it ended up working, so let me just explain once I... Yep, that looks about right. So vector. So I remade my case. It looks like importing the results of 0.5 was just causing issues. So instead, I just changed my control dict in here to 0. In here, I just went to control dict, changed my start time to 0, left everything else the same, and I just got the same results here. So it looks like that's all this tutorial has to offer for us. Yeah, this was a great introductory simulation for OpenFOAM. Gave you a good foundation of what each of the source code case files means. So if you enjoyed this, leave a like. I might post some more content on OpenFOAM. I might do the next tutorial here. Instead of 2.1, 2.2, which is the stress analysis of plate with hole. So if you guys want to see that, then I can just go through the same thing. I know this isn't crazy, it's just a walkthrough through the tutorial, but you can see me go through it and try and follow along. Hope you enjoyed. See you guys next time. Peace out.